guys. So this is going to be our 15.8 lesson on spherical coordinates. So this is the first time I'm actually trying to record a lecture via Zoom like this, so we'll see how it goes. So spherical coordinates are our other option for three-dimensional polar coordinates. So in the previous lesson, we talked about cylindrical coordinates, where our coordinate system was sort of polar in 2 dimensions and rectangular in the 3rd dimension. This time, when we talk about spherical coordinates, we're basically going to be polar in all 3 dimensions, okay? So the spherical coordinate system or the spherical coordinates, rho, theta, phi of a point P in space are the following. So this P looking Greek letter is what we call rho. It's actually a Greek R. This is the distance from the origin. And so it makes sense then why we'd be using a Greek R, talk about distance from the origin. So that's basically like a radius, okay? So if I'm going to start drawing my 3-dimensional coordinate system here, I'm going to kind of talk through each coordinate as I draw it. And I also have posted a little animation as to how these 3D coordinates work, which I think is very useful to look at rather than just looking at these static pictures. Okay, so we have our x-axis, our y-axis, and our z-axis. And so this first coordinate rho, I'm going to draw in blue, and this will be the distance out from the origin. So maybe perhaps we draw, just some distance out from the origin. Or actually, let's do it this way. So let's draw a random point in 3D space. So maybe it's up here. And this point is point P with coordinates rho, theta, and phi. So I'll use 3 different colors for the coordinates so you can kind of see how these work. So if we're thinking about the straight line distance from the origin to this point, that is our coordinate rho. So if I'm thinking about how long this distance is, I don't know why my pen is being funky. So this distance between the origin and our point is our coordinate rho. And then theta is basically like the polar coordinate theta. So that's going to be the angle between the positive x-axis and the projection of this, line segment, the origin up to P onto the xy plane. So theta is basically like if I were to project this thing down into the xy plane, then theta is this angle in here from the positive x-axis over to that projection. Okay. And then phi is sort of the same thing, but with the z-axis. So it's the angle between the positive z-axis and this dotted black line between the origin and the point P. So phi is this angle in here. Okay, so that is a little introduction to the spherical coordinate system. A couple of other things that we typically think about when we're doing this. So rho we usually take to be positive or non-negative, so 0 or bigger. We don't use a negative rho value. And when we talk about phi, we want to use angles between 0 and pi, okay? And that's just so we don't end up with points that have all of these different names for the same location. And so just like cylindrical coordinates, spherical coordinates are useful in particular problem situations. So for cylindrical coordinates, it was useful when we had symmetry about an axis. For spherical coordinates, it's going to be important for symmetry about a point. Okay, so spheres have symmetry about a point. So we're looking at objects that have similar situations going on. Okay. So as I said, some examples of symmetry about a point. First, we have the sphere. So I think that one's pretty obvious. That one's literally as symmetric as you can get. But we also have two more examples of symmetry about a point. So half planes fall into this. So this is a rotational symmetry about the origin, but with respect to the XY plane. So for this half plane, you can imagine a sheet of paper being held up, and you're just kind of turning it around the z-axis, but that gives this thing rotational symmetry about the origin just in the XY plane. And then for the half cone, that's another example of symmetry about a point. So once again, we do have symmetry about the origin, but we're sort of doing it with respect to that angle phi instead of theta. Okay, so we're thinking about keeping that angle phi between the z-axis and, you know, the point that we want constant. And then if we rotate that around the z-axis, we get a cone. So spheres, half planes, and cones are your big three cases where spherical coordinates can be very useful. Okay, so just like we did with cylindrical coordinates, we're going to look at converting spherical coordinates to rectangular coordinates. So you're going to notice that these look a lot like polar coordinates, but a little bit different because we have that extra angle in there, phi. Okay, so our x coordinate will be rho sine of phi cosine of theta. Y will be rho sine of phi sine of theta. And z will be rho cosine of phi. And we can relate all three coordinates together using rho, so that's just your equation of a sphere right here. Okay, so let's practice. So let's find the rectangular coordinates of the spherical point 2, comma, pi over 4, comma, pi over 3. So the first thing we're going to want to do is think about our x, y, and z coordinates. So we know from above that x is equal to rho sine of phi cosine of theta. And we know that these coordinates are rho, theta, and phi. I'm going to write those right there since we're new to this type of coordinate system. Y is equal to rho sine of phi sine of theta. And z is equal to rho cosine of phi. All right, so now that I have my formulas written out, I can go ahead and let me see if I can zoom in on this really quick. Oh, there we go. All right. So I can go ahead and plug in my coordinate values. So for x, we'll have 2 times the sine of pi over 3 times the cosine of pi over 4. So this one's going to be 2 times root 3 over 2 times root 2 over 2. The 2 will cancel out with one of these, and so we end up with the square root of 6 over 2 for our x coordinate. Our y coordinate is quite similar, so we have rho is equal to 2, phi is equal to pi over 3, and theta is equal to pi over 4. So we get 2 times the square root of 3 over 2 times the square root of 2 over 2. The 2's cancel out, and once again, we get the square root of 6 over 2. And thirdly, we have rho cosine of phi, so that's just 2 times the cosine of pi over 3, which is 2 times a half, which is just 1. So our rectangular point will be the square root of 6 over 2, square root of 6 over 2, and 1. And my highlighter's gonna Duh. All right, so that's my rectangular point. Now we can go backwards. We can find the spherical coordinates for a rectangular point. So that's what we're going to do in the next example. So what we're going to do for this second example, like I said, we're going to start in rectangular coordinates and go to spherical coordinates. So this time we're going to pull out our equation of a sphere to get our rho value. Okay, so the first thing we're going to do is use the fact that rho is equal to, or rho squared, is equal to x squared plus y squared plus z squared. So I can substitute these values, 0 squared plus 2 root 3 squared plus -2 squared. And that gives me 0 plus 4 times 3 plus 4, which is 16, which means that rho is equal to the square root of 16, which is 4. Okay, so I have my rho value. Now what I'm going to do with this, since I know rho and I know my x, y, and z coordinates, I can sort of solve for theta and phi using some of that information. So the first one I'm actually going to start with is the z coordinate, and I'll explain why. So the formula for z is rho times the cosine of phi. So the reason I'm starting with the z coordinate is, remember that we know the coordinates x, y, and z, and we know rho at this point. So starting with the z coordinate, it has the least number of variables, so I can actually solve for phi given that I know z and rho. So z is equal to -2 and rho is equal to 4. So now I want to find the angle phi. So dividing by 4 gives me -1/2 is equal to the cosine of phi, which means that phi must be 2 pi over 3. And so I'll explain why this is. So I'm looking for some angle with a cosine value of -1/2. But if you remember up at the top, I wanted phi to be between 0 and pi. All right, so remember that condition right there. So that means that I'm looking for the angle in the top half of the unit circle with such a cosine value. And the only one that fits that is 2 pi over 3. So far, I know rho and I know phi. The last coordinate that I need to find is theta, which I can do with either x or y. I'm going to opt for x because x is equal to 0, which might make it a little easier. So again, you could use either, but I'm going to opt for x here. So we have x is equal to rho sine of phi times cosine of theta. Plugging in what I know now, x is 0, rho is 4, phi is 2 pi over 3, and I want to solve for theta. All right, so we have 0 is equal to 4 times the sine of 2 pi over 3 is root 3 over 2 times cosine of theta. So I can divide 0 by that coefficient, which still just gives me 0 is equal to cosine of theta. And so that means that theta must be pi over 2. Okay, so why did I want theta equal to pi over 2? So let's go back up to the top and refresh our memory on what the stipulations about theta were. So theta was the angle between the positive x-axis and the projection of that line segment between the origin and our point P onto the xy plane. So in order to know which angle I want to pick for theta, sometimes it's useful to think about what quadrant, so to speak, the x and y coordinates would be in. So where am I going with this? So we know that if we want the angle where cosine is equal to 0, we know that on the unit circle, there's two angles that fit that criteria. So there's pi over 2 and there's 3 pi over 2. But if we think about our x and y coordinates, so let's imagine this projection onto the xy plane. If we want the coordinates 0, 2 times the square root of 3, that would fall on the positive y-axis. So this would be the point 0 times 2, or not times, but 0, 2 root 3. And that falls on the positive y-axis, which corresponds to the angle pi over 2 rather than 3 pi over 2. Okay, so that's how we pick between those two possible angles. So now that I have all three coordinates, I can go ahead and write my spherical point. So rho is 4, theta is pi over 2, and phi is 2 pi over 3. So this is my spherical point. Right? So that is how we convert between rectangular and spherical coordinates and vice versa. So next, we're going to start looking at some calculus now that we understand how to go between the two. So our theme with these multiple integrals has been to think about a rectangular box, right? And in spherical coordinates, it's no different, except our box is just not rectangular. Instead of a box shape, so to speak, we're going to end up with a spherical wedge. Okay, so you can imagine that that sort of looks like, you know, like a curved square or something like that. Well, hang on, let me draw a better picture of this. So we've got sort of this square shape, but on a sphere, so it's a little curved. And it goes in toward the center of our sphere. So that would be our spherical wedge. So you can imagine like if you had a cake ball, I guess, and you wanted to cut a wedge out of like a piece of cake out of a cake ball, it would sort of look like that. That's a little weird to think about that. So how do we define this spherical wedge? So as a set, we can talk about it being the set of spherical points, rho, theta, phi, where rho is between numbers a and b, theta is between angles alpha and beta, and phi is between angles c and d. Okay. Now there's a few stipulations on this. We do want our rho value to be positive, so we say that the letter a is greater than or equal to 0. We also want to stay within one rotation of the unit circle. So alpha and beta better not be more than 2 pi apart. Otherwise, I would be going more than one rotation around the circle. And likewise with phi, we want to keep it within a half circle. Okay, so we want to keep c minus or d minus c less than or equal to pi. Okay, so how do we get our triple integrals now? So this formula is quite a doozy. It's not fun to write down in your notes because it barely fits on one line. So I kind of had to squeeze that in there. So if we actually look at this formula though, we notice that it's like really similar to when we did polar coordinates, just we have 3 coordinates to substitute and we have a different thing multiplied at the end. So we don't have that nice RD theta anymore. We've got a different factor that we need to multiply by. But we see all of these things popping up, right? We've got rho sine phi cosine of theta. We've got, I'll do a few colors here. We've got rho sine of phi sine of theta. And we've got rho cosine of phi. So these things come straight from our conversion formulas that we just talked about. So this is the coordinate x, this is y, and this is z. And the only difference between this and polar, pretty much, is we just have this different factor that we multiply by on the end, okay? But we take our order of integration to just be the order of the coordinates. So we go for d rho, d theta, d phi, right? Okay, so let's practice this with an integral. So we're going to evaluate the triple integral over the unit ball b of e to the x squared plus y squared plus z squared, all raised to the 3 halves. So if this problem was not in the spherical coordinate section, my first indication that we're dealing with a problem that lends itself to spheres is number one, you're integrating over the unit ball, which is a sphere. As you get into higher and higher maths, they start calling spheres balls. And as you get into higher dimensions, they just become the ball of dimension whatever, or the hypersphere, sometimes they're called. And in addition to that, I noticed this exponent right here literally contains the equation of a sphere. So those are two indicators that this is a good spherical problem. And so it's worth doing the conversion. Okay. So let's look at how to set this up. So the first thing I'm going to do is sketch a picture of what B should look like. So keeping in trend with our other notes, step one is I'm going to analyze my region B. And step two is we're going to set up and solve the integral. Okay. So if I sketch my region B, this is a sphere. So we get our axes down. So this is the x-axis, y-axis, and z-axis. And so this is a unit ball, so radius 1. And it's in that three-dimensional coordinate space. So that's kind of hard to do when it's all the same colors. So maybe I'll swap colors here for the sphere versus the axes. Okay, so that's kind of our outline. Then we've got it kind of doing that. Like this. So again, colored pens are kind of helpful here. So that's a sketch of our sphere. So now we want to think about bounding the three spherical coordinates, which are rho, theta, and phi. So we have rho, we have theta, and we have phi. So first, maybe it's nice to think about rho. So remember, rho is our radius of the sphere, which this is a solid sphere. So the radius can go anywhere from 0 out to the boundary, which is 1, because we have a radius of 1. So rho is going to be bounded between, come on, computer, don't spaz on me, please. Okay, so rho is between 0 and 1. Theta, because in the XY plane we have a complete circle, this is going to be 0 to 2 pi. And phi is going to be between 0 and pi. So that's a little bit counterintuitive. The natural thing, I think, is to want to think about phi the same way as theta. That's where watching that animation on spherical coordinates will really make it make sense why we don't want to take the whole circle around. We only want to take the half circle for phi, because if we're already rotating in the XY plane, it actually gets taken care of. So one way to think about that is actually like, those paper lanterns that you get like for parties and stuff, and they start out flat and you sort of like expand them around. They start out as a half circle and you sort of expand them around to make the lantern. That's kind of what you're dealing with here with the sphere. That's why phi, we only want to take 0 to pi, because it starts out as a half circle, and then we use that 0 to 2 pi in theta to fill out the whole sphere. So think about that a little bit, but it's hard for me to just describe with my hands on a video. Okay, so now we're going to set up and solve the integral now that we have all three of our variables bounded. So the triple integral with respect to b of e to the x squared plus y squared plus z squared to the 3/2 dv will be equal to the integral from, well, actually, let me just leave my bounds open for now. So that x squared plus y squared plus z squared is just rho squared, and that's raised to the 3/2. Then the integrating factor, that weird number that we multiply by, is rho squared sine of phi. d rho, d theta, d phi. So that's why I just keep those variables in the order that they're written in a spherical point. So there's no confusion there. But now we know the order in which to put our bounds on the integrals. So the phi bounds will be the outermost integral because phi is the outermost variable there. So our last integral will be 0 to pi. The middle integral corresponds to theta, so we have 0 to 2 pi. And the first integral corresponds to rho, so we have 0 to 1. We can make this look a little bit better before we integrate. So we have 0 to pi, 0 to 2 pi, and 0 to 1 of e to the rho cubed times rho squared sine of phi d rho d theta d phi. Now, one thing to notice about this problem is all of our bounds are constant, and we've got a bunch of functions multiplied together that use different single variables. So like in the e, I don't see two different variables, right? I just see rho. In sine, I only see phi. I don't see any of the other two variables. So actually, to make this sit a little better with my brain, and maybe yours too, we can actually rewrite this even more different. So we can move the sine of phi all the way to the outer integral, like this. And we can leave the middle integral as is, because I don't see any thetas roaming around. And we can write that first integral. Okay, so now we just have a product of integrals, and that makes it a little easier for me to look at it at least. Okay, so let's see what we're going to do here. So maybe we start with integrating sine of phi first. So the integral of sine of phi will be negative cosine of phi, and that's evaluated from 0 to pi. Then I'm going to multiply that by the integral from 0 to 2 pi of, this looks like a u substitution problem to me. So we're going to say u is rho cubed. And so du is 3 rho squared d rho. So I can divide by 3 and get that 1/3 times du is equal to rho squared d rho. And now I have everything I need to make a u substitution in rho. So my new bounds on my integral are still 0 to 1, because when I cube 0, I still get 0. And when I cube 1, I still get 1. Okay, so I am changing my bounds, but they do turn out to be the same. And this integral will now turn out to be 1/3 e to the u du d theta. All right, so if we keep going with this, this would be negative cosine of pi plus cosine of 0 times the integral from 0 to 2 pi of 1/3 e to the u evaluated from 0 to 1 d theta. So we have negative, let's see, cosine of pi is -1. So we have negative -1 plus cosine of 0 is 1 times the integral from 0 to 2 pi of 1/3 e minus 1. So e to the 0 is just 1 d theta. And so finally, this turns out to be 2 times 1/3 e minus 1 times theta, evaluated from 0 to 2 pi. So our final answer for this is 2/3 times e minus 1 times 2 pi. And if you wanted to simplify that just a little bit more, you could say it's 4 pi over 3 times e minus 1. Okay, so that's an example of a integral worked with spherical coordinates. And again, just like with polar coordinates and cylindrical coordinates, in this case, it not only made our function easier to integrate by going to spherical coordinates, but it also made the bounds a whole lot nicer. So because we went to spherical coordinates, we were able to get constant bounds instead of really nasty square root bounds in 3 variables. Okay, so that's the good thing about it. All right, we have one more example to do. So we're going to use spherical coordinates to find the volume of the solid that lies above the cone. Z equals the square root of x squared plus y squared, and below the sphere, x squared plus y squared plus z squared is equal to z. Okay, so just like before, the first thing I'm going to do is sort of get a sketch of what this region looks like. So if I sketch my 3D axes, we've got x, y, and z. So I've got a cone, z is equal to the square root of x squared plus y squared. So that is actually, it's that cone with the 45-degree angle that we did in the previous lesson. I'm going to draw that in red. So we get something that looks like this. We've got the center of the cone there. It's kind of at a 45-degree angle with the origin. So that is z is equal to the square root of x squared plus y squared. And if I wanted to draw this sphere, this is a sphere. If we can actually figure out what this looks like. So maybe let's do that real quick. So I'll do that in blue. So if we have x squared plus y squared plus z squared is equal to z, I can move that z over to the other side and get x squared plus y squared plus z squared minus z is equal to 0. Completing the square in z, we get x squared plus y squared plus z squared minus z plus 1/2 squared is equal to a fourth, because 1/2 squared is a fourth. So that's how much I added on the left side. So I have to balance it out on the right. So this sphere is x squared plus y squared plus z minus 1/2 squared is equal to 1/4. So what this tells me is that the center of this sphere is 0, 0, 1/2 with a radius of 1/2. So the radius would be the square root of a fourth. So what this tells me is that I have a sphere with a radius of 1/2. Okay, so it looks sort of like this. It's actually going to intersect the cone right there. It fits perfectly. Okay, and so we know that this point is also the center of the sphere. Okay, so this is our x squared plus y squared plus z squared is equal to z. So now I've got a pretty nice picture. And I can kind of figure out my spherical bounds on this region. So what is the region that we're actually trying to integrate or find the volume of? So what we're trying to do is get the volume of this ice cream cone shape in here. So we've got this right here. And so it's kind of like it's above the cone, below the sphere. So we've got this solid shape that's it's like the shape of an ice cream cone. It's got a cone with a little scoop on top. Okay. So how do we think about this? Well, I want to, let's see. Yeah. Okay. So I think theta and rho are pretty easy to get. It's going to be the, how do I want to do that? Never mind. Phi and theta will be pretty easy to get. Okay, so let's think about theta first. All right. So for theta, remember we're thinking about the angle in the XY plane. So basically the angle of rotation around the Z axis. So since this is a fully circular object, we have a cone with a little like half circle on top. Theta is between 0 and 2 pi because it has a full rotation around that Z axis, okay? Now, the other two coordinates can be a little tricky. So for phi, maybe phi is the next easiest one, I think, even though it's the newest coordinate because we're only just talking about spherical coordinates today. But phi is basically the angle that your graph opens up from the Z-axis. Okay, so you're starting vertical, and then your graph opens up some angle phi. So we want to think about what angle is that cone from the Z-axis, basically. And we know from previous work that this is a 45-degree cone, but we can always figure it out again, too. So to figure out that this is a 45-degree cone, let's see what I can do. I can say, well, I can make a substitution. I can make a spherical substitution for Z is equal to, well, let's see, I'm doing this for the cone, so I'll do it in red. So we start with Z is equal to the square root of x squared plus y squared. And if we use our spherical formulas, we know that Z is rho cosine of phi, and x is rho sine of phi, cosine of theta, and y is rho sine of phi, sine of theta. So I can simplify this a bit to get rho cosine of phi is equal to the square root of rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta. And I get my classic cosine squared plus sine squared. So I can think about this as just that common factor between the two terms. So this will end up being rho cosine of phi is equal to the square root of rho squared sine squared of phi, which gives us rho cosine of phi is equal to rho sine of phi, which means cosine of phi equals sine of phi. And so the only angle between 0 and pi, where the cosine value is equal to the sine value, is if we have phi equal to pi over 4. So we're going to take our phi bounds to be between 0 and pi over 4. All right, so the last thing we need to think about are those bounds on rho. Okay, so if we're thinking about how that works, I think we need to do a little bit of analysis with the sphere. So if we're looking at our picture, I think it's pretty obvious that the smallest this radius can be is 0, because at the center of the sphere, the radius is 0, right? It's just a point. The hard part is the upper bound, okay? So what we want to think about is, let me see how to explain this. So let's think about our sphere in spherical coordinates, okay? So if we think about the equation of the sphere in spherical coordinates, we get that rho squared is equal to the spherical value of Z, which is rho times cosine of phi. Dividing by rho on both sides gives us that rho is equal to cosine of phi. So this gives us the equation of our sphere in spherical coordinates, and it gives us a way to write rho in terms of one of the other variables. So this is why this is going to be our upper bound on rho. Okay, so the upper bound on rho is just going to be cosine of phi. So now I think we're ready to set up our integral. So now to set up the integral, I'm going to have the integral of 0 to 2 pi. Let me write that again. That was messy. Okay, 0 to 2 pi times the integral from 0 to pi over 4. And wants to spaz again. Times the integral from 0 to cosine of phi. And then what I want to do is I want to integrate the function of the, what do I want to do? Oh, okay. So how we're going to pick the function that goes in here. So if we think about what this was in rectangular coordinates, that's what we need to do. So we're going to have the triple integral. Okay, we first learned about triple integrals. We said they can compute volumes for us. So it's just the triple integral of dv. So we have nothing inside of the integral. Okay, so it's just some region E, let's say, of dv. So the same thing happens when we go into spherical coordinates. So the only thing we're going to be left with is that special integrating factor that our function is normally multiplied by. So that rho squared sine of phi, and then we'll have d rho, d phi, d theta. So I think here I switched the order of phi and theta, which is okay because they're both constant bounds. So we can't switch rho. That one needs to go first because its upper bound is cosine of phi. But as far as phi and theta, doesn't really matter. So now if we think about integrating this, let's see what I can do. So if I want to do, well, let's see. I can actually pull the sine of phi out to the second integral. So we have 0 to 2 pi of 0 to pi over 4 sine of phi times 0 to cosine of phi of rho squared. And really I should have, okay, hang on. Let's do one little eraser in here. So we're kind of separating all of these things to go with their respective integrals. So even the d theta, I can pull out to the first integral. So we'll have 0 to 2 pi of d theta. Then we'll have 0 to pi over 4 sine of phi, d phi. So let me see if I can squeeze that in there. And then we'll have rho squared d rho. Okay, so we have 3 integrals all multiplied together. And that kind of, again, makes it easier to think about because we can think about it piece by piece instead of having to think about it all at one time. Okay, so let's see. Oh, wait. I'm sorry. Okay, scratch one little thing. So we can't pull the sine of phi out because our bound on rho contains a phi. So we actually do need to keep those together. So my bad there. Okay, so we have rho squared sine phi d rho d phi. But we can pull the d theta all the way out to the theta integral. Okay, I apologize about that. Okay, so as far as our theta integral goes, the integral of d theta is just theta from 0 to 2 pi. Then for the rest of this, we'll have the integral from 0 to pi over 4. First, we're integrating with respect to rho. So we'll have 1/3 rho cubed times sine of phi, evaluated from 0 to cosine of phi d phi. So this is just going to be 2 pi times the integral from 0 to pi over 4 of 1/3 times cosine cubed of phi times sine of phi. So 0 is just going to, plugged into rho is just going to make the whole term go to 0, so I'm not super worried about it. And so we end up with this integral. Now, I want to integrate this with respect to phi. And one really nice thing is I think this is just a nice u substitution, okay? So let's suppose that we take u to be cosine of phi, which means du will be negative sine of phi d phi, which means negative du is equal to sine of phi d phi. Okay, so making the u substitution then, this is 2 pi times the integral from the cosine of 0 is 1, and the cosine of pi over 4 is root 2 over 2. This is 1/3, well, negative 1/3, times u cubed du. Okay, so keeping on here, we've got 2 pi times times negative 1/3 times 1/4 u to the 4th, evaluated from 1 to root 2 over 2. So this will be negative 2 pi over 3 times 1/4 times root 2 over 2 raised to the 4th minus 1 raised to the 4th, which will give us, let's see, that's going to be negative pi over 6 times, okay, root 2 over 2 raised to the 4th. So that'll give us 2 factors of 2, which is 4, over 16 minus 1. So we end up with negative pi over 6 times 1/4 minus 1, which is negative pi over 6 times negative 3 over 4, which gives us, see, that's a 2, so positive pi over 8. And so that is our integral. So that is the end of lesson 15.8. Please let me know if you have any questions.